Welcome to the session on finite differences. Numerical analysis is a branch of mathematics which leads to approximate solution by repeated application of 4 basic operations of algebra. The knowledge of finite differences is essential for the study of numerical analysis. In this session, we introduce few basic operators. First one is forward difference operator. Let y equal to f of x be any given function, and let y naught, y1 etc. yn are values of y at the points at the equidistant points x naught, x1 etc. xn. Then we can find the differences y1 minus y naught, y2 minus y1 etc. yn minus yn minus 1. These differences are called first forward differences. Which are denoted by delta y naught, this is delta y1 etc. in general delta yn minus 1. The symbol delta is called the forward difference operator. Delta is an operator. The difference of these first differences are called the second forward differences, which are denoted by delta square y naught, delta square y1, delta square y2 etc. That is, delta square y naught equal to delta of delta y naught, that is equal to delta of delta y naught is y1 minus y naught, that is equal to delta y1 minus delta y naught, that is y2 minus y1, delta y1 is y2 minus y1 minus delta y naught is y1 minus y naught, that is equal to y2 minus 2 times y1 plus y naught. Delta square y1 equal to delta of delta y1, that is equal to delta of delta y1 is y2 minus y1, that is equal to delta y2 minus delta y1, which is equal to delta y2 is y3 minus y2 minus delta y1 is y2 minus y1, that is equal to y3 minus 2y2 plus y1. Here delta square is called the second difference operator. Delta square is again an operator which is called the second difference operator. Similarly, we can define the higher order differences and higher order operators. Now, the difference table. It is a convenient method for displaying the successive differences of a function. The difference table is as follows. If x naught, x1, x2, x3, x4 are equidistant points and y0, y1, y2, y3, y4 are the corresponding functional values, we can draw the difference table like this. This is the values of x, values of y. Now, the third column is the first differences. That is, the first difference is y1 minus y0, y1 minus y0, that is delta y0. We use delta y0 here. In between y1 and y0, we write delta y0. Here delta y1 in between y2 and y1. Here delta y2, this is delta y3. Now, the second differences. Next column is second differences, that is delta square y0. In between these two, we mark delta square y0. Here delta square y1, delta square y2. And the third differences, next column is for third differences, delta cube y0. In between these two, here delta cube y1. And the fourth difference is in between these two, that is delta 4 y0. This table is called the diagonal difference table. The first term in the table is y0. It is the leading term. This is the leading term. And delta y0, delta square y0, etc. are called the leading differences. Next, we have an example, that is construct a difference table for the function y equal to f of x. That is equal to x cube plus 2x plus 1 for x equal to 1, 2, 3, 4 and 5. The first column is x, that is 1, 2, 3, 4 and 5. Here y of f of x, that is y. For x equal to 1, y is 1 plus 2 plus 1, that is 4. For x equal to 2, it is 13. For 3, y equal to 34. For x equal to 4, y equal to 71, sorry 73, and for 5, for x equal to 5, y is 136. The first differences are here 13 minus 4, that is 9. We mark 9 in between 13 and 4. Next difference is 34 minus 13, that is 1, 21, 21. 73 minus 34, that is 39. Next difference is 63, that is 136 minus 73. The next difference, that is second differences are 21 minus 9, that is 12. 39 minus 21, that is 18. 63 minus 39, that is 24. These are the second differences. Third differences are 18 minus 12 is 6, 24 minus 8. that is also 6. The fourth difference, delta 4y is 0. This is the corresponding difference table. If 5 values are given, then there are 4 differences, forward differences. In another notation, we can write the forward differences. That is, if the values of x are a plus h, a plus 2h, etc., and the corresponding values of y are f of a, f of a plus h, f of a plus 2h, etc., then we can define the first difference as delta f of a as f of a plus h minus f of a. Using this definition, we can write delta f of a plus h, that is equal to f of a plus h minus f of a plus h, that is equal to f of a plus 2h minus f of a plus h. Similarly, delta square f of a can be written as delta of delta f of a, which is equal to delta of delta f of a is this f of a plus h minus f of a. This is equal to delta f of a plus h minus delta f of a. But delta f of a plus h is f of a plus 2h minus f of a plus h. Delta f of a is f of a plus h minus f of a, minus of minus is plus f of a. That is equal to f of a plus h, sorry, f of a plus 2h minus 2 times f of a plus h plus f of a. This is the second forward difference. Similarly, we can define the higher order differences. In general, we can write the definition as delta f of x is equal to f of x plus h minus f of x. This is the general definition. Here h is the interval of differencing. Using this definition, we can write delta square f of x as f of x plus 2h minus 2 times f of x plus h plus f of x. Similarly, we can write the higher order differences. Now, let us see some properties of forward differences. Properties. First property is if f of x is a constant function, then delta of f of x is 0. That is, if f of x is a constant function, then delta of delta f of x equal to 0, that is delta c equal to 0. By definition, we have delta f of x is equal to f of x plus h minus f of x. Since f of x is a constant function, f of x plus h also equal to c. Therefore, this is c minus f of x is c equal to 0. That is delta c equal to 0, where c is a constant. The second property is the forward difference operator delta is distributive. That is delta of f of x plus or minus g of x is equal to delta f of x plus or minus delta g of x. Again, by definition, we can write delta f of x plus g of x, the left hand side, equal to f of x plus h plus g of x plus h minus f of x plus g of x. This is by definition. That is equal to f of x plus h minus f of x plus g of x plus h minus g of x. By definition, this is delta f of x and this is delta g of x. That is delta of f of x plus g of x is equal to delta f of x plus delta g of x. Similarly, we can write delta f of x minus g of x is equal to delta f of x minus delta g of x. This is the second property. And the third one is, if c is a constant, then delta of c into f of x is equal to c into delta f of x. Just the c, the constant c can be taken outside. By definition, we can write the LHS delta of cf of x as c f of x plus h minus c f of x, that is equal to, c can be taken outside c into f of x plus h minus f of x, that is equal to c into, this is by definition delta f of x. That is delta of c times f of x is equal to c times delta of f of x, which is the third property. And the fourth one is delta raised to m into delta raised to n. Delta raised to m of delta raised to n f of x is equal to delta raised to m plus n of f of x, where m and n are positive integers. We have delta raised to m of delta raised to n f of x, that is the left hand side, is equal to delta raised to m means delta into etc. into delta, that is the m times delta of n times delta. Delta raised to n means n times delta, n times of f of x, which is equal to delta m times into delta n times means delta etc. into delta, total m plus n times of f of x, that is equal to delta raised to m plus n of f of x. This is the fourth property. Similarly, we can prove delta of f1 of x plus f2x plus etc. plus fnx, that is equal to delta of f1x plus delta of f2x plus etc. plus delta of fnx. Delta of f of x into g of x, the forward difference of a product, which is equal to f of x into delta of g of x plus g of x into delta of f of x. This is the product forward difference of a product. And the forward difference of a quotient is delta of f of x divided by g of x is equal to g of x into delta of f of x minus f of x into delta of g of x, all divided by g of x into g of x plus h, g of x into g of x plus h in the denominator. These are the properties of delta. Now, we have an example. Evaluate delta of e raised to ax, delta of e raised to ax. Here f of x equal to e raised to ax, then by definition delta of e raised to x equal to f of x plus h minus f of x, means e raised to a into x plus h minus e raised to x. That is equal to e raised to ax plus ah minus e raised to ax. That is equal to e raised to ax into e raised to ah minus e raised to ax. E raised to x can be taken in common, that is e raised to x into e raised to h minus 1. Delta square of e raised to x. Second question is to evaluate delta square of e raised to x. This is equal to delta of delta e raised to x. That is delta of, by definition delta e raised to x is e raised to x plus h minus e raised to x. That is equal to delta of e raised to x into e raised to h minus 1. That is e raised to h minus 1 into delta of e raised to x. That is equal to e raised to h minus 1 into delta e raised to x is e raised to x plus h minus e raised to x by definition of delta f of x. That is equal to that is e raised to h minus 1 into delta e raised to x is e raised to x plus h minus e raised to x, that is e raised to h minus 1 into this is again e raised to h minus 1 into e raised to x, like this. that is e raised to h minus 1 the whole square into e raised to x. Now, the next operator is the operator e, that is the shifting operator, is called the shift operator, just denoted as e of f of x. This is equal to f of x plus h. The second shift operator is e square of f of x, that is equal to e of e f of x, that is e f of x is f of x plus h, which is equal to, by this definition, this is equal to f of x plus h, that is f of x plus 2h. Similarly, in general, e raised to n f of x can be defined as e raised to n f of x is equal to f of x plus nh, f of x plus nh, and e raised to minus n f of x is equal to f of x minus nh. The properties of shift operator are e of f1 of x plus f2 of x plus etc. plus f1 of x is equal to e of f1 of x plus e of f2 of x plus etc. plus e of fn of x. And e of c times f of x can be written as c into e of f of x, where c is a constant. E raised to m of e raised to n f of x is same as e raised to n of e raised to m f of x. Both are equal to e raised to m plus n f of x, where m and n are positive integers. Now, if n is a positive integer, then e raised to n of e raised to minus n f of x is equal to f of x itself. If y naught, y1 etc., yn are n values of f corresponding to the points x naught, x1, x2 etc., xn, then the shift operator can be defined as e y naught equal to y1, e y1 equal to y2 etc., e square y naught equal to y2. In general, e raised to n y naught equal to yn. This is another notation for shift operator. Thank you for watching this session. We will meet again in another session. Thank you all.